I'm Salonik Resch, and the paper I'm presenting is on endurance of processing in non-volatile memory. The story of this paper is as follows. Modern applications, such as large-scale machine learning algorithms, require large amounts of data. And this data is difficult to store in memory, and this leads to a performance bottleneck known as the memory wall. Processing in memory architectures are an appealing solution to this problem because in some cases they can entirely circumvent this memory wall problem. Specifically, non-volatile processing in memory promises extreme energy efficiency in addition to all the other benefits. And so this has led to a proliferation of non-volatile processing in memory accelerator designs. However, non-volatile devices have a limited endurance, and that means we can only write to them a certain number of times before they fail. For standard memory architectures, this isn't really a problem because there are standard methods to mitigate this problem, such as load balancing and write cancellation. Unfortunately, as we show in this paper, processing in memory makes this problem a lot more difficult to solve by introducing additional complications. First, processing in memory will greatly increase the number of writes for a given application. Traditional architectures only need to write to non-volatile memory in order to store their final results. Conversely, processing in memory, since it's doing the computation in the memory itself, all of its operations will write to non-volatile memory. And this results in orders of magnitude more writes. For example, a 32-bit multiplication has 150 times more writes in a processing in memory architecture. Additionally, since we're doing the computation in memory, we can't use methods like write cancellation to improve the lifetime. Secondly, processing in memory makes load balancing a lot harder. In standard architectures, we can easily redirect writes to different locations to balance out the usage. Processing in memory architectures introduce additional constraints, such as requiring the operands to be aligned in memory, which makes dynamic load balancing much harder to achieve. But even if we were able to do perfect load balancing, it still doesn't even come close to fully compensating for the increase in the write counts. While the write count can increase by 150 times, our simulations show that load balancing can at most improve the lifetime by about 3x. So, software and architectural level changes are going to be insufficient to solve this endurance problem. Processing and memory architectures are going to critically rely on device level performance. And current technology is not quite at the level where it makes processing and memory feasible, but there are experimental evidence and device projections that suggest this may be possible in the near future. If you would like to learn more about this problem, please come see my full presentation in Session 2B on Monday at 3:15 p.m. Thank you.